Café Scientifique is a monthly series of expert-led discussions on science and culture presented by the Bell Museum of Natural History. For more information about the Bell Museum, or to find out about upcoming Café Scientifique programs, visit bellmuseum.org or find us on Facebook and Twitter.
Good evening and welcome to Café Scientifique. Hey, all right, yes. Okay. And now here's Leah.
Thank you, Kevin. And my name is Leah Peterson. I'm the Adult Programs Coordinator at the Bell Museum of Natural History. Thank you so much for being here for Café Scientifique tonight. I don't want to take too much of your time because Michel has an awesome talk planned for you, and it's got a lot of content, and I want you to be able to get involved with all that content with the Q&A at the end as well. So without any further ado, tonight's speaker has long been interested in making the results of his research on the history and philosophy of modern physics accessible to a broader audience. Michel Janssen is a professor in the history of science, technology, and medicine at the University of Minnesota, where he has been known to offer a popular seminar titled Einstein for Everyone, and that's how I came across him in the first place. He is also one of the editors of the Cambridge Companion to Einstein, which likewise aims at a broad audience. And he can tell you a little bit more about that if he likes. Tonight, we talked a little bit about the structure that's going to work for him for the cafe. The first half of the cafe is going to be a lot of conceptual physics stuff, so you have to pay attention. But no equations, you said, right? No equations. The second half is going to get into the personal life of Einstein and talk about him as a person. And Michel would love to have you hold your questions until the very end. So we'll do a Q&A at the end because he knows that you could ask any question and he could talk for literally probably the rest of the night about whatever that thing is. So remember, we are making a podcast tonight. It is available at University iTunes and through the Bell Museum of Natural History website at the Café Scientifique webpage. And it'll be up in about a week or two. And we encourage you to check that out. But in the meantime, these folks are getting seated, and we'll welcome Michel Janssen up to the stage.
Thank you very much. Thank you, Leah. Thank you, Kevin, for inviting me, and thank you all for coming. I'm delighted to see so many people. Everybody knows this guy, right? The old sage. But a student of mine in my Einstein for Everyone class had a project where a few years ago she went over campus and showed people pictures of famous scientists. And everybody recognized the old sage, but when she held up a picture of Einstein, at age 26 when he was doing all this important work, no idea who that is. Same with Darwin, by the way. So as one of my mentors used to say, John Stachel, the founding editor of the Einstein Papers Project, he says, of all the myths about Einstein, the most persistent one is that he was born at the age of 50. Okay? And now, the problem with that is that a lot of what we know about how the young Einstein did his phenomenal work, most of the work happened between 1905 and 1920, comes to us from what the older Einstein said about this. And I want to argue that the older Einstein gave a somewhat misleading impression about what the younger guy was up to. And there's a very famous passage from a talk he gave in Oxford, the Herbert Spencer lecture in 1933. I'm struggling here to stay close enough to the mic and being able to read these quotes to you. So Einstein says, our experience hitherto justifies us in believing that nature is the realization of the simplest conceivable mathematical ideas. I am convinced that we can discover by means of purely mathematical constructions the concepts and the laws which furnish the key to the understanding of natural phenomena. Experience, of course, remains the sole criterion of the physical utility of a mathematical construction, but the creative principle resides in mathematics. In a certain sense, therefore, I hold it true that pure thought can grasp reality as the ancients dreamed. And here we're thinking about people like Pythagoras and Plato. Now, if you think about it, this is a very, very peculiar and radical view, right? Basically, it's saying you can come up with physics just putting a paper bag over your head, writing down pretty mathematics, and if it's pretty enough, right, you're very confident, you're Einstein, that the Lord made the universe just like that. Okay? Now, that is not, as I hope to show you, how Einstein proceeded. But it's I think it's a very sort of part of a widespread picture of about how Einstein went about doing his physics. And so there is an anecdote that is often used to illustrate this kind of very cavalier attitude towards empirical data. And that is a story that was told by this woman Ilse Rosenthal-Schneider, who happened to be with Einstein when confirmation of his general theory of relativity came in 1919. So he received this telegram by my countryman Hendrik Antoon Lorentz saying that Eddington had just confirmed general relativity. And so the woman like Ilse Rosenthal-Schneider asked Einstein, well, Professor Einstein, what would you have done had the result come back negative? Okay? And Einstein supposedly said, I would have felt sorry for the dear Lord, but the theory is correct anyway. Okay? Now, so again, it makes for a great anecdote, but I do think that it's a caricature of how Einstein really thought about the importance of empirical results. So here's a much better example of how Einstein thought about empirical data. So this is in response to an experiment by Walter Kaufmann in 1907. And Kaufmann was the first experimentalist to respond to Einstein's special theory of relativity in 1905. And of course, part of that is equals mc squared. So what Kaufmann was in effect checking was that if you look at electrons in beta decay, which are very fast moving electrons, up to 90% the speed of light, you would expect that their mass is going to increase dramatically, right? The mass goes up with energy. A fast-moving electron has a lot more energy than one at rest, so you would expect the mass to go up. And indeed, that's what happens. But Einstein's theory was not the only theory that predicted it. There was several other theories that also produced a formula, a little different from Einstein. And it looked as if those theories actually agreed better with the data than Einstein's own. And so this is what he said. So he says, Abraham and Bulger's theories, those were the two guys now forgotten who had these theories, yield curves that are significantly closer to the observed curve than the theory of relativity. However, he added, the probability that their theories are correct is rather small, in my opinion, because their basic assumptions are not suggested by theoretical systems that encompass largest complexes of phenomena. So this is so for Einstein, this was the important part, right? Science is not just about curve fitting. It's not about, drawing a line through a bunch of points. No. You have a satisfactory theory if that theory can account for a whole variety of phenomena, right? And so in that sense, Einstein does care about that the theory actually accounts for the phenomena. He just cares less about, what happens in the third decimal place. Okay? All right. So now, to go back to this talk that he gave in 33 in Oxford, he actually does add two disclaimers. And the first disclaimer is actually in the very first sentence of the talk. So Einstein says, if you want to find out anything from a theoretical physicist about the methods they use, I advise you to stick closely to one principle. Do not listen to their words. Fix your attention on their deeds, right? And then he proceeds to tell people how you do physics. Okay? So the other thing is that later on in the talk, he sort of indicates that the way in which a researcher is reflecting on his own methodology, right? And it's just the way that he regards its past and present may depend too much on what he hopes for the future and aims at in the present. So this is at a period when Einstein is working on, I'll talk a little bit about that later, is unified field theory. And in fact, this whole speech is one big manifesto for the methodology that he used for this unified field theory, which again is different from the way that he found the stuff that he's famous for, like relativity theory, special and general, and early contributions to quantum mechanics. All right. So, unfortunately, with Einstein dead and gone, right, it's hard to look at his deeds. So no matter what we're going to do, we're going to have to look at his words. But what we can do is look at words that were written like a little closer to when he was doing his most important work. Right? And that's what I intend to do. And study the papers in which like he published like his most important results and try to infer from those like how he got there. So a very important document that I think is much more revealing about how the young Einstein, how the young Turk did his work, was an article that he wrote in the London Times in 1919. And this article was solicited when he became like an overnight celebrity, like because of like the confirmation by Eddington of general relativity. And in that article, he makes a distinction between two types of theories. One is called a constructive theory. The other one is called like a principle theory. And a constructive theory, that is probably what you think about when you think in general about, what it would take to develop like a physical theory. Like what you do is you develop kind of a model that accurately describes some features of reality. So the example that Einstein gives is what is known as the kinetic theory of gases, where you think of a gas as just a collection of billiard balls like bouncing around in a box, and the pressure is like produced by the billiard balls like hitting the walls, the temperature like is given by the kinetic energy of these balls as they move around, and you have a good theory if that model gives an accurate description of the measurements that you perform on an actual gas. Okay? That's one way of proceeding. Now the other way is what he calls like a principle theory. And there you don't worry so much about a model, you just like take some very general like experimental truths, such as it is impossible to create like a perpetual motion machine, and see how that constrains your theorizing. So this is like the approach that underlies a theory that Einstein greatly admired, namely thermodynamics. Right? So the science of thermodynamics is based on like these fundamental laws that essentially say that you can't create anything out of nothing. Right? There's a certain directionality in the way like processes like develop, but they don't give you a model like on how to picture that. Right? And so Einstein was really the master of these principle theories, but sort of ironically, he preferred like the constructive theories. So in that same article in 1919, he wrote, like when we say that we have succeeded in understanding a group of natural processes, we invariably mean that a constructive theory has been found which covers the processes in question. Right? So the first question then becomes, given that he preferred like these constructive theories, why is he bothering with these principle theories in the first place? Okay, and here, like I'm going to quote, you may find this dubious because I'm not quoting like the old sage, but I think this time the old sage actually said something sensible. So in his autobiographical notes, which Einstein with typical self-deprecation referred to as his own obituary, he says like by and by, and he's talking about the discovery of special relativity, he says, by and by, I despaired of the possibility of discovering the true laws by means of constructive efforts based on known facts. See the word constructive here. The longer and more despairingly I tried, the more I came to the conviction that only the discovery of a universal formal principle, note the word principle, could lead us to assured results. The example I saw before me was thermodynamics. Okay? So, in a word, in a slogan, a principle theory for Einstein was kind of a physics of desperation. Like, if you have no idea what like a constructive theory for these phenomena, what a model would look like, do the next best thing and try and formulate constraints on what these models are going to be. And Einstein was absolutely phenomenal at doing that. One of the areas where this approach was particularly successful, and I don't have time to talk much about this because I will tell you a little bit about relativity theory. But one of the areas where this was most successful was in Einstein's early contributions to quantum theory. Remember, like, the most famous line, of course, about quantum theory is God doesn't play dice, but that is way later. In fact, he was one of the main architects of quantum theory and just didn't like the direction it took in the mid-20s. And so I would argue that Einstein made important contributions to quantum mechanics for precisely as long as he realized that he had no idea what the constructive theory for these phenomena looked like. Okay, so but he was very good at just accepting, like, so in 1909, like my favorite example, he just looked at the data and says, look, I don't know how this is going to be, but the next theory of light is going to be a theory that is going to combine wave theory and particle theory. You figure it out, but that I know for sure. Okay, so and so like a sort of a nice anecdote, sort of illustrating like Einstein's despair at not understanding the quantum world, and that's what why I have this picture here. So this is the Tyne Church in Prague. Like many people have been to Prague. It's a beautiful, beautiful, beautiful church. And so Einstein's office was not here, but Einstein's office was overlooking like a psychiatric ward. And what he saw was there were people like milling about, like, you know, every lunchtime, you know, like, and so when he was showing the office to his successor, Einstein was there for a little while, and then he was called to bigger things. He became like a full professor at his alma mater, the ETH, like the famous Polytechnic in Zurich. So he was showing like his office to his successor, Philipp Frank, who became one of Einstein's early biographers. And Philipp Frank relates this anecdote that Einstein is pointing to these people like walking around and is saying to Frank, those are the madmen who do not think about quantum mechanics. Okay. So, given how good Einstein was at this, like I'm interested in the question, how did he find his principles, right? Because that's what it hinges on. Like, you know, you need to find these principles. And so you can distinguish a few ways in which he did this. So one is like, you know, what I call the humdrum way, right? So, you know, every attempt so far to create like a perpetual motion machine has been unsuccessful. Well, let's assume that it is impossible to create like a perpetual motion machine, right? Now, that if science worked like that, we'd all be Einsteins, okay? It typically doesn't work like that. So what did Einstein do? What made him special? So I like to call this like Einstein's magic wands. And this magic wand number one is that, like other greats, so my former boss, Alan Shapiro, is a Newton specialist, and like he told me the same thing about Newton. These guys have the broad overview. They're not like narrow specialists looking at one particular area. No, they compare something happening over there, something happening over there. You can say the same thing about Darwin, and see that, you know, and Einstein, and seeing that it's not quite right here. In fact, like something over here and something over there like violently clash. But they're both these things seem to be right. So now, like, you know, something is going to have to give, right? And then by locating what is going to have to give, you learn something. Okay, so this is like Einstein is very effective in using that both in relativity theory and in quantum. But I'm most interested in a different magic wand, which I call magic wand number two. And that is like, you know, in fancy speak, to exploit like the explanatory weaknesses of existing theories. In less highfalutin terms, it's ask pesky why questions, right? The kind of questions that your kids like drive you nuts with. You know, why is this? Why? Oh, but why? Why? You know, and so there's this endless regress. So there's an art to this, right? You need to know when and why question is going to have something, going to tell you something useful, and when it's not. And Einstein was very good at coming up with like very good why questions. And I'll give you a few examples of those. And so like both special relativity and general relativity in the end got off the ground by Einstein asking like what in hindsight looked like a very obvious why question. So here's my first example. And it's this. It's the thought experiment that opens Einstein's 1905 paper on special relativity. The paper is called On the Electrodynamics of Moving Bodies. Of course, it's now famous for new ideas about space and time, but the ideas about space and time are there to solve like a problem in electrodynamics. So Einstein is looking at two experiments that look very similar but are different according to the reigning theory. In the first experiment you have like, so the setup is that you have a magnet and you have a conductor, right? A wire loop with an ammeter in it. And in the first experiment what you're going to do is you're going to move the magnet. There's going to be like a changing magnetic field felt by this loop. And Faraday's induction law says that if you have a changing magnetic field, you get an electric field, and the electric field is going to make this electron go around the loop, and that will cause like the ammeter to register. If the thing stops, the ammeter goes back to zero. That's why you don't see like anything here. It's a real ammeter here. So now you look at a different experiment, same components, but now what you're going to do, look carefully, you move the conductor. Okay? And once again, you see the ammeter like, you know, register a certain current and, you know, go back to zero. The exact same current as it shows on the left. But now the story is very different. The magnet is at rest. Okay? There is no changing magnetic field. So Faraday's induction law does not kick in. There is no electric field. Yet, the electrons are going around the loop. Why is that? Because like a moving electron experiences a force from a magnetic field called the Lorentz force. And that turns out to do the exact same thing, right? Now, you look at this and you think like, well, I'm not that impressed that, after all this blah, blah, that, this is the same, you get the same result, because to me it looks like the same experiment just described from two different perspectives, right? But in the reigning theory of the day, these experiments are very different, because like people thought that electric field and magnetic fields are carried by some material medium called the ether, right? And obviously the ether cannot at the same time be at rest with respect to the magnet and with respect to the conductor. Okay? So on that theory, it is sort of a cosmic coincidence that these very different experiments like give the same results. Why, Einstein is asking? Well, it just happens to be the case, like an impatient theorist at the time would say. But Einstein, doesn't like that, and so his answer to that is actually very radical, right? So he says, this is the same situation looked at from two different perspectives, and a lot is going to follow from this. So by the time he's through with the first paragraph of that article, he says, look, there can't be an ether. Right? Because it cannot be at rest with respect to both these things. Out. This was the basics of a lot of 19th century physics, and Einstein disposes of it in one paragraph. And then he says look, if you really believe that it's the same thing, and in one case you're talking about electric field and magnetic fields, in the other case you're talking only about magnetic fields, then it can also not be true that there really is an electric field and a magnetic field. What you really have is a unified electromagnetic field that for one observer is going to look like a combination of an electric and a magnetic field, and for another observer it's going to look like a pure magnetic field. Okay, so now I hope this is going to work. So this is basically getting right to the heart of the principle of relativity, and I don't know of any expression of the relativity principle better than this song by Dave Mason.
There ain't no good guy, there ain't no bad guy. There's only you and me, and we just disagree.
Ooh, Leah told me it's like a rock star up here. Anyways, so here is Einstein himself, describing, emphasizing how important that idea was to him, right? So in an article he wrote in 1920, he says, the idea that we would be dealing here with two fundamentally different situations was unbearable to me. It's very emotionally charged for Einstein, right? The existence of one electric field was therefore a relative one, dependent on the coordinate system used, and only the electric and magnetic field taken together could be ascribed some kind of objective reality. Now, what is true for electric and magnetic fields is also true for space and time. And that was put most convincingly by Einstein's former math teacher, Hermann Minkowski, in Zurich. So Minkowski was very surprised that Einstein came up with this theory because, as he once put it, Einstein was a lazy dog who skipped his classes. Einstein, not to be outdone, returned the favor by calling Minkowski's beautiful work superfluous learnedness. But this is now what every physicist knows as the special theory of relativity. It's called Minkowski spacetime. And so Minkowski introduced this in a very famous talk in Cologne in 1908, the year before he died. It was published posthumously. And this is how he starts. The views of space and time which I wish to lay before you have sprung from the soil of experimental physics, and therein lies their strength. This is all coming from electrodynamics. They are radical. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Right? And Minkowski actually goes on to complain. He says, the word relativity postulate seems to be very feeble. The postulate comes to mean that only the four-dimensional world is given, but that the projection, the way it breaks down, the projection in space and in time may still be undertaken with a certain degree of freedom. There ain't no good guy, there ain't no bad guy, right? We just disagree. All right. So that's how he got started on special relativity. Remember, it got off the ground by asking this why question that the existing theory could not answer. He did the same thing with general relativity. And here, like he went back even further and looked at this, very famous thought experiment by Galileo and the Leaning Tower of Pisa. I've been told that if you go up there these days, that it has a sign at the top and says, "Dear tourists, please do not drop any objects from this tower." So, of course, the point of this experiment is that all these objects fall with the same acceleration. And so this is something that Newton had noted and was scratching his head about. And he explained this like in a rather sort of like complicated way, saying, look, there's two effects here. Like gravity is pulling on stuff, and there is something called gravitational mass that is a measure for how susceptible an object is to gravity. If it's going to be like, if it is going to have more of the gravitational mass, the gravitational pull will be bigger, right? And so you think, oh, but then it's going to fall faster. But there's another property called inertial mass, which is a measure of how much does a object resist acceleration. Okay? And so if that mass is getting bigger, then it's going to resist more strongly. And it so happened, another cosmic coincidence, that those two properties that seem to have nothing to do with each other, like susceptibility to gravity and resistance to acceleration, are exactly equal to one another. Right? So no matter what the mass is, it will always fall in Newtonian theory with the same acceleration. Why? Well, why? We know that this is the case. Shut up. Like this. Right? But this is not. Like Einstein is saying. Look. There's got to be some. Like something behind this, right? I mean, nature is giving us like a clue with a capital C here. We need to figure out what that is, right? And so initially, Einstein thought, right, that this would allow him to do something that he desperately wanted, namely to extend the relativity principle from like uniform motion to accelerated motion. And that turned out to be wrong. I'll show you a little bit like what the idea is. But like he thought about this for a long time, and after about a decade, like he figured out what nature is truly telling us here, and that is that inertia and gravity are, so to speak, two sides of the same coin. And I'll try to explain that slogan a little bit too. So this is the conceptually most complicated part of my story. So pay close attention. So story starts here, like in what Einstein again reflecting in 1920 about him sitting at the patent office in 1907. And he says, at this point came to me der glücklichste Gedanke meines Lebens. It's typically translated as the happiest thought of my life, but it's more accurately translated as sort of the best idea of the most fortunate thought of my life. So what he says is then came to me the happiest thought of my life, using the standard translation. Like the electric field generated by electromagnetic induction, right, the reference to that experiment that I explained to you, the gravitational field only has a relative existence. Because for an observer, freely falling from the roof of a house, no gravitational field exists while he is falling. Of course, when he hits the pavement, it's a different story. So, but let's do what they do in these cartoons, right? And just, let's stop things like in the middle here, right? And so Einstein is seeing this guy falling, right? Or imagining that he's seeing the guy falling. And so he is at rest in the gravitational field and the other guy is accelerating. But he says, well, I can extend the relativity principle to like accelerated motion. Special relativity only handles uniform motion with constant velocity. I can extend it to accelerated motion if I allow two observers to agree to disagree on whether there is a gravitational field or not. So Einstein in this situation is going to say, there is a gravitational field, I'm at rest, and the other dude is accelerating. But for the other dude, he doesn't feel the gravitational field. Right? I mean, so Einstein still had to imagine this, but of course now we're all familiar with this because this is a situation that people in the space shuttle are in constantly. If you're just free falling in a gravitational field, you're weightless. Okay? So for the other dude, it's a little different. So he's hovering here, right? Doesn't feel a gravitational field. So he says there is no gravitational field. And this other dude that I'm seeing, like the somewhat odd-looking dude, like he is accelerating in like some spaceship, like accelerating upwards. Okay? And so you can see that for like if you think about like what happens to like Einstein if he were really in the spaceship accelerating upwards, that would feel the exact same way than sitting at rest like in his office. Okay, so this then is what Einstein thought, like, okay, so I'm now able to reduce in a way all acceleration to sort of gravitational fields. Again, this doesn't quite work out if you work out the details of this. But what he did get after a period of thinking about this for about a decade was that this idea sort of unifies inertia and gravity into something that we now call the inertial gravitational field. Okay? So it's essentially like a unification of space-time and the gravitational field. And here's how it works, roughly. So particles, to speak about this metaphorically, particles get their marching orders from two different instances. On the one hand, they get it from the space-time structure. And the space-time structure tells them, thou shalt move in a straight line at constant speed, regardless of thy constitution, unless forces tell thee otherwise. That is like a very, nice way of expressing the law of inertia. And then there is like assorted forces, and those forces tell the particle, thou shalt deviate from thy straight line, following the specific instructions given to thee based on thy constitution. Okay, so the first one is for everybody. The second type of instruction depends on like the constitution of the body. So if you're talking, for instance, about electric forces, the electric forces only have jurisdiction over particles with electric charge. Right? Now, what Einstein noted is that there's one force, the gravitational force, that is every bit as democratic, as universal and indiscriminate as the space-time structure, right? Because of this, like in Newtonian terms, because of this equality of inertial and gravitational mass, like, that force tells all the particles to move the same way. And that allowed Einstein to move over the instructions, like coming from the gravitational force, from, the department of assorted forces to the department of the space-time structure. Right? And so now the space-time structure sort of incorporates gravity, right? So a different way of saying this is that gravity becomes part of the fabric of space-time. So space-time is now generally curved, right? And particles do what we all try to do, go straight in a crooked world. Okay? And so what Einstein did with this is he atoned for a grave sin of Newton. Because Newton, like this is not present in Aristotle, but Newton had like made a very sharp distinction between space on the one hand and gravitational forces on the other. Einstein says, no, these two things belong together, right? And so, like he could have told Newton, thou shalt not, I blew my own line. Thou shalt not tear asunder what God has united. Okay? And this inertial gravitational field, right, combining these two instructions, that will split differently for different observers, like the one, like Einstein sitting in his office and the guy falling from the roof. And remember the quote when Einstein says, like, the gravitational field is relative, just like the electric field, like in that example with the magnet and the conductor. Right? I mean, those passages are actually from the same page in that article. All right. So what I hope to have indicated here to you is how tremendously successful Einstein was by following this principle approach. Like getting to like the principle of special relativity, getting to what is called the equivalence principle, the connection between inertia and gravity, by asking these why questions and like, using like other strategies to get at these principles. Now Einstein himself must have realized that, he was phenomenally good at this and better than anybody else at the time. So now the question changes a little bit. Like, I showed you earlier, like Einstein prefers like constructive theories, but why? He is so good at these principal theories. Why not keep doing that? And I think I have an answer. This is speculative, of course, but I think it's this, right? So if you look at it the way I want you to look at this, what special relativity does mainly is to combine, to unify the electric field and the magnetic field into one electromagnetic field. What general relativity does is it unifies space-time and gravity, or inertia and gravity, into one inertial gravitational field. What would be the next step? Right? And Einstein, at this point, thought that he knew, God's plan for the universe, right? So he was not like, this is not a physics of desperation anymore. Like he knows, like, what kind of theory he should look for. Can just out of curiosity, can you think of like, what would you do next if you've established this much?
Unify electromagnetism and gravity.
That's right. Exactly right. Right. So so you've unified these two things now. Grand unify the whole thing. And that's exactly what Einstein does the rest of his life. Okay. So without much success. In fact, with so little success that one of his most important biographers, my countryman Abraham Pais, once said that it would not have made one bit of difference had Einstein gone fishing in 1920. Okay? Now that's unkind, right? Because you still have very important work, like Einstein's most cited work, like the Einstein-Podolsky-Rosen papers, 1935, and is the basis for all these applications of entanglement in quantum theory these days. But there is a grain of truth to this. I mean, this never led anywhere. So Einstein is now very confident that, he knows this is how God made the universe, and by golly, I'm going to develop like a theory modeled on general relativity, a constructive theory, and then, I'm just going to keep my fingers crossed that this same theory will also at someday replace this theory of quantum mechanics that I don't care for. Okay? And so, So that's how we get back to constructive theory. All right, so let's take a deep breath now. So remember, I started out with this story about like what he's saying in Oxford in 1933. So clearly he's talking about models there, but the most important thing he was saying is that the guide should be mathematics. Right? So I still need to answer okay, he went from principle to constructive, but why rely so much on mathematical simplicity rather than on evaluating data? And there's a number of factors. One of the things you learn when you do history of science is that it's very, if you hear a story where it's sort of monocausal, be suspicious of it, right? I mean, typically there's many things going on at once. So one factor, an important factor, is that in 1915, the Göttingen mathematician David Hilbert almost beat Einstein to the punch in putting the finishing touches on general relativity. And how did Hilbert do that? Hilbert was not a physicist. He just wrote down the pretty mathematics and didn't worry at all about the physics. A lot of the physics had already been done by Einstein. He had just made one thing that was wrong, and mathematics told Hilbert this should be it. And almost stole Einstein's glory. And Einstein clearly thought, that's not going to happen to me again. Okay, so I can play this game too. So some people believe that's all there is to it, but I don't. I think there's another factor, and that is the factor that I want to talk to you about the rest of this session. And this is that Einstein, around this time, has a very serious midlife crisis. And I'll show you some of the problems, and you'll agree with me that this is a midlife crisis of gigantic proportions. And so it's in that situation that Einstein starts to put into practice what he has been preaching for a long, long time, namely to use physics to get away from it all, to escape, from the dreariness of everyday life, and so the solace he finds is in building these beautiful mathematical constructs. Right? So clearly, there, you don't want to roll up your sleeves and start dealing with messy empirical problems. No, you built beautiful mathematical castles in the sky. So I think this is also a part of it, right? And I emphasize a part of it. Okay, so we're going to shift gears now, right? You've suffered through the conceptual bit, no more physics for the rest of the evening. So sit back and relax. So I first need to tell you a little bit about a side of Einstein that you may not be familiar with, right? I mean, you look at that guy here, the world's most lovable egghead, this avuncular type, And, yes, that's just partly true, but that's not the whole story. So I want to show you another side of Einstein. And this comes from a novel by the very minor novelist Max Planck called The Redemption of Tycho Brahe. And so the Max Planck claim to fame, as many of you will know, is that he was the editor of Kafka, right? I mean, Kafka asked Brahe to burn all his writings, and Brahe, thank God, didn't do that, which is why we have all this wonderful stuff by Kafka. Brahe himself, beyond that, was not a very good writer. But he met Einstein. He met Einstein when Einstein was in Prague. right? Remember, like he showed his office to his successor, so around 1912 he's there. There's a lot of speculation about whether Einstein and Kafka have met. It's unclear whether they did. They certainly did not make had not a big impact on each other. And so Max wrote this novel called The Redemption of Tycho Brahe. Tycho Brahe is like one of the famous sons of Prague. So if you've been to this Stein church, you will have seen like the grave of Tycho Brahe, right? So just like a little bit about Brahe, like this like a 16th century astronomer. What you see here is them digging up his grave because like there's some discussion about how he died. So when he died, they thought it was because of kidney stones, but there's like high levels of mercury were found like in the hairs of his mustache. And so there's two possible explanations, both of them very amusing, both of them fairly far-fetched. So the first is that it came from like the metal prosthesis he made of his nose. So he famously had his nose chopped off in a duel, right? And he had prostheses made of various metals. So maybe like, there was some mercury in there. Or the other possibility is that he was actually poisoned, mercury poisoned. And one of the main suspects, and people have tried to make a lot out of this, is that he was poisoned by Kepler, the other great astronomer, that Kepler wanted to get access to like all sorts of things. So, I don't believe either of these stories, but there you have it. That's why they're digging. Now, why do I bring this up? I want to draw attention to this passage in The Redemption of Tycho Brahe. And Brahe told people that he modeled the figure of Kepler on Einstein. And this is not at all the avuncular, lovable egghead that you think of when you hear Einstein. So this is what Brahe writes. He says, the tranquility with which Kepler applied himself to his labors was to Tycho almost superhuman. There was something incomprehensible in its absence of emotion, like a breath from a distant region of ice. He had no heart, and therefore had nothing to fear from the world. He was not capable of emotion or love. Wow. Well, you think, like Brahe saw Einstein like, for an hour, right? So how seriously should we take this? Now, interestingly, like Einstein, like Einstein ended up in Berlin. He went there in 1914. And one of his colleagues there, Walter Nernst, actually read this novel. And so here you have a picture of Einstein with his Berlin colleagues in the late 1920s. And I like to think that this is the moment when Nernst made this observation. And he read the book and he says to Einstein, "You are this man, Kepler." And Nernst didn't know that Brahe had based Kepler on Einstein, right? So there was something very recognizable about this character in this book that people who knew Einstein very, very well recognized. Okay? And so this is as surprising to me as it may be to you, because like this goes completely against the lovable egghead image that we have of Einstein. But there is something to this. So with that, preamble, let's look at this, and let's look at like the development of this idea that you use physics to get away from it all, right? To use Einstein's own terms from his autobiography, to get beyond the merely personal. So this is Einstein as a very young man. So here he is, lodging with the Winteler family. This is when he flunks the entrance exam to the ETH, and they tell him like, well, you need to do some like high school equivalency, and then you will be admitted. So like, before you now think that I'm endorsing this myth that Einstein was a poor student, he was very, very good at math and physics, but he didn't apply himself to anything that didn't interest him, right? And so he flunked the bits on history and French, right? And so he needed to like bone up on those in order to be admitted. But they were sufficiently impressed with what he did in physics and math to tell him, look, if you take care of that, you're in, right? So he's lodging with this family, and he has a great time here. So he hated like the Prussian high school system in Munich with sort of this drill sergeant mentality. But this system in Switzerland, staying with this family where the guy was the headmaster of the school, wonderful. And on top of that, like he had like what probably was his first girlfriend, Marie. So this is Marie. So don't get confused because he's holding hands with the mommy, not with the daughter. This confusion will like play a role a little later on too. So this is what Einstein wrote to to essentially his landlady, Pauline Winteler. Dear Mommy, I cannot come to visit you at Whitsuntide. I have already caused much too much pain to Marie. It fills me with a peculiar kind of satisfaction that I now myself have to taste some of the pain that I brought upon the dear girl. It's all pretty condescending, but that's par for the course. Strenuous intellectual work and looking at God's nature are the reconciling, fortifying, yet relentlessly strict angels that shall lead me through all of life's troubles. And yet, what a peculiar way this is to weather the storms of life. In many a lucid moment, I appear to myself as an ostrich. One creates a small little world for oneself, and as lamentably insignificant it may be, in comparison with the perpetually changing size of real existence, one feels miraculously great and important, like a mole in a self-dug hole. Okay? This is part of like what I'm getting at. But look, you know, this is written in 1897. Einstein was born in 1879. I wonder how you would like it if I go through your correspondence that you wrote at the age of 18, right, to make grand pronouncements about your psychology. Okay? So if this is the best evidence I have, right, I mean, like, you know, you should be skeptical. Of course, I have more. But let's keep moving. So, like, Einstein goes now to the ETH, and there he meets like his first wife, Mileva Maric, a fellow student at the ETH, and we have some of the correspondence between them, right? And so, so it's interesting to read you a few quotes from this. So Einstein writes in 1897, it's a really screamingly funny life that I'm leading, completely in Schopenhauer's sense. So it's completely irrelevant what the philosophy of Schopenhauer is, but Schopenhauer is responsible for, all you need to know is responsible for this idea of like getting away from it all, right? And I'll show you other examples like showing that. To think of all the obstacles that these old Philistines put in the way. Philistines was another favorite term of Albert and Mileva, right? It's the two of them against like, you know, the mean old world, the Philistines. And so here's another one like 3 years later. You too don't like the Philistine life any longer, don't you? He who tasted freedom cannot stand the chains any longer. How lucky I am to have found in you a creature who is my equal, who is as strong and independent as I am myself. Right? Now, that whole sort of happy-go-lucky attitude wouldn't last very long. So, so this is a postcard that Einstein sent to his family from Splugen. Splugen is like a pass across the Alps connecting Italy and Switzerland. And this is the most important Einstein document that I can claim to have discovered myself. I found this in a shoebox. I mean, I was led there, okay? So, like I was told, like, you know, this guy, like a descendant of Einstein's friend Michele Besso, had a shoebox with all sorts of material. And I could look through this material, and I found this postcard. And it immediately struck me because of the date. So, and because of the name Splugen. You know, my boss at the Einstein Papers Project, the world's leading specialist on Einstein's biography, Robert Schulman, had drilled this into me. I immediately recognized what this was. And like you will probably also recognize it when I give you one other date. So the next important date is January of 1902. Can you guess what happened at Splugen? Count the number of months between those two dates. Okay, yes, so this is when Albert got Mileva pregnant. This was a big scandal. This was effectively the end of Mileva's studies, right? So it's a rather tragic affair. She had to leave Zurich, go back to Serbia to give birth there. And despite tremendous efforts of like Einstein scholars, like all trace of this girl disappears. We didn't even know about her until like Robert Schulman discovered the love letters between Albert and Mileva, where they talk about this, right? And so all we know is that the girl was born on this date, that they intended to name her Liesel. Other than that, this was a well-kept family secret. And this, actually was already the beginning of the end of that relationship. But, you know, like they finally, against the strong objections of Einstein's parents, are getting married. In 1903, they moved to Bern, where Einstein becomes like a patent clerk, right? So during his miracle year, he's not a professor, he's like a patent examiner, third class, and he's doing the groundbreaking work sort of under the table, you know, like during the work. But he performs his duties like well enough that in 1906 he does get a promotion at the patent office all the way from a patent examiner third class to a patent examiner second class. So in 1909 he he quits and then starts his meteoric rise up the academic ladder. So at that point, like, you know, they have like, so they have one son, Hans Albert, known as Adu in the family, became like an hydraulic engineer, moved to the US. And then a second son, like Eduard, known as Tete, and, you know, he is like falls into this sort of stereotype about like, you know, there's a thin line between like, you know, madness and genius. So this kid, unfortunately, was diagnosed as a teenager with schizophrenia and spent most of his adult life in institutions. Now, I hope you saw the special effect that I worked in, that, you know, that the young Mileva gets fader and fader and fader in all of this. And that, you know, she is basically just banned back to the kitchen. And so Einstein is running this club with a few of his friends, like known as the Olympia Academy, where they discuss everything under the sun. And even though these discussions are sometimes held at Einstein's own house, the records indicate that she wasn't even part of these discussions anymore, right? So she's really like has given up all her own ambitions of like becoming a scientist, and all the stuff that you saw in this early correspondence has long evaporated. Now the whole thing comes to a crash when Einstein like leaves Zurich to take up like a very prestigious job in Berlin. And so there is this document. I hope you can see it. So I want to focus on part of it, but I just want you to take it in. So there's some text here, some equations here, some doodles there, some big folded thing. And we can date this document to about July of 1914, about 3 months after Mileva and the boys joined Einstein in Berlin. So I want to now focus on this part of the document. Okay, I'll blow it up for you a little bit. And so you see here, like here you see the word Bedingungen. That means like conditions. And if you look at it, you see A, 1, 2, 3, B goes here, then C. What is this? Is this the outline for some paper that Einstein is working on? Not quite. This is what it is. You make sure that my clothes and laundry are kept in good order and repair, that I receive my 3 meals regularly in my room. B, you abstain from all personal contact with me unless absolutely required for reasons of social decorum. C, you commit yourself to observing the following points in your dealings with me. 1, you are neither to expect intimacy from me nor to reproach me in any way. You are to stop talking to me immediately when I ask you to. You are to leave my bedroom as well as my study immediately and without protest when I ask you to. Okay? And a bit of other text that is here is essentially recording some of Mileva's reaction to this. And so here, this bit, and so we think that Einstein is just quoting Mileva here, where she says, like, read it to your family as well. They have nothing else to do anyway. And there another bit, like, they should know that there are others who are interested in what a spectacle he's making of himself, the famous man. And then at the very bottom, Einstein writes this, commenting on these comments of Mileva, bad jokes, schlechte Witze. Okay? Now, probably the most shocking thing about this document is that indirect evidence suggests that Mileva was willing to accept these conditions. Okay? So she was staying with a friend, Fritz Haber, and his wife, Clara Haber. And so Einstein, like, you know, sent over these conditions, and like from Haber, he heard back, she's willing to abide by those. But you can see this is a marriage that is completely on the rocks. So a couple of weeks after this document, Mileva and the boys actually like went back to Zurich, right? So they agreed to a separation and then agreed to a divorce. So that's why Einstein gave his Nobel money to his wife, not because she helped him invent special relativity, as some people want to claim, but because, like, you know, he needed to obtain a divorce, and this was like his way of paying her off. Okay. So you're beginning to see that, you know, not everything is like, hunky-dory in Einstein's life at this point. So part of the problem was that when he went to Berlin, he had actually had an affair already with the woman who became his second wife. And so it's his cousin, and it's even better than that. It's both his first and his second cousin. And you wonder, how can that be, right? Well, it's very easy. Their mothers were sisters, and their fathers were first cousins. So that makes, right? So on one side, first cousins, on the other side, second cousins. They did not have kids together, right? So don't worry. So these 2 young women that you see here are the daughters of Elsa Einstein-Löwenthal from a previous marriage, right? So you have like Ilse and Margot. And so here's like another picture of the two of them. And so eventually, like Einstein married Elsa, and for a short while he became actually a very snappy dresser. Okay. But this did also not happen without like some further disturbances. So here's another document that I want to show you. And so I'll blow this up. And I'll tell you what it is. It's a letter from Ilse Einstein, one of the daughters of Elsa, to this guy Georg Nicolai. Okay? And I'll translate one bit for you. It says here at the top, I don't know whether you can read this. Vernichten Sie bitte diesen Brief sofort nach dem Lesen, which means please destroy this letter immediately after you read it. Clearly that didn't happen. Now, how do we get this letter, right? So this guy Nicolai was a physician to Elsa Einstein, and Ilse probably was one of his like romantic conquests. He kept like a long book of these. And Nicolai became like sort of a pacifist, you know, like and influenced Einstein in that direction. And a Michigan historian, Wolf Zülzer, wrote his biography and found this letter, like in this. And so he sent the letter, a copy of the letter, to the people in Princeton of the Einstein Papers Project. The people at the Einstein Papers Project dispatched a team of lawyers to Michigan to get Zülzer to fork over the original so they could throw it into the fire. But Zülzer knew his rights. Zülzer knew that he had the property rights on that document, just not the copyright. So he knew that he could do anything he wanted with this document, including like, you know, wiping his behind, as long as he did not publish it. That he could not do because he did not have the copyright. So he sent the lawyers away, right? And so then the question becomes, who has the copyright? Well, obviously the author, like in this case, Ilse Einstein. All right. Now the people at the Einstein Papers Project we want our hands on the document, not to destroy it, but to publish it, right? And so Ilse Einstein died young, and her husband married a much younger woman. He died in the 60s, and so the copyright now goes from Ilse Einstein to the husband's second wife. The woman was still alive in the mid-90s when I joined the Einstein Papers Project, and my boss, Robert Schulman, had been trying for many, many years to sort of butter up to this woman who was living in New York on the Upper East Side to get her to, sign over the rights. And Robert told me that he lost track of the amount of stale cookies and the gallons of lukewarm tea that he had to consume in order to gain the trust of this woman, right? This is what Einstein scholars need to do to get their hands on this material. Okay? So while I was there, at one point, like the woman calls up and says, like, Herr Schulman, I heard that people are going to publish this document. Das müssen Sie unterdrücken. You must suppress this. And Robert says, like, well, there's nothing I can do. I would advise you to sign the rights over to us because we're not going to sensationalize it. Okay? So she did. 2 weeks later, Robert comes into my office again, and he says, like, well, wouldn't you know? The woman just died. Not a moment too soon, because she may well have changed her mind. And so, let me just hold this up. So the letter is now part of Einstein's collected papers, like thanks to Robert's effort. All right, so I hope you're sufficiently curious now what is in this letter. This is what Ilse Einstein has to say. You will recall that we recently talked about Albert's and Mama's marriage, and that you said to me that a marriage between Albert and me would be more appropriate. Until yesterday, I'd never given this any serious thought. Yesterday, however, the question suddenly came up whether A should marry Mama or me. Albert refuses to make a decision. That's my favorite part. Either way, fine with me. He's prepared to marry either me or Mama. I have never felt any desire to be close to him physically. For him, this is a different matter, at least lately. He recently told me how hard it is for him to control himself. Einstein obviously would roll over in his grave knowing that that is part of his collected papers. So I'm hoping you're beginning to see this is a guy with a bit of trouble. Okay? Now, on top of all of this, there's a world war going on. Okay? And I hope you saw... We did another nasty thing. We put this picture on the cover of this volume. And the guy in the picture is Fritz Haber. So Fritz Haber is famous for coming up with the process to use nitrogen out of the air, right? And so this is great to produce fertilizer and all that. But he also was the one who helped the Germans with poison gas in the First World War. He personally oversaw the use of chlorine at the Second Battle of Ypres in Flanders in Belgium, right? And it got so bad that his wife, right? You see here, 1817, 1915. That is no coincidence. She committed suicide just a few weeks after her husband had directed the troops, the German troops, in Ypres with this poison gas. Okay, so you see Einstein somewhat awkwardly standing next to this guy. I mean, this is the guy who is showing them the ropes in Berlin, right? This is the guy who's trying to mediate between him and Mileva, right? And it's, for a budding pacifist, right, it's not such a great look, right, to stand next to a guy who, basically is guilty of war crimes, right? Now, the situation for Haber would end bad and tragically. So Haber, like Einstein, was Jewish. And so when the Nazis came to power, the fact that this guy was a decorated war hero did him no good. And so in 1933, he resigned from the institute that he had founded and left to take up a position in Palestine, died on his way in Basel, and then to make matters worse, in the 1920s, that same institute had worked on something that they called cyclone, which we now know as cyclone A. And of course, a modification of that, cyclone B, was used in the gas chambers. And so the rest of Haber's family perished in the death camps of the Nazis. Now, so here is a picture of one of my favorite painters, John Singer Sargent, capturing sort of the misery that Haber brought upon the British troops fighting on the Western Front in World War I. Okay, so remember, so this is also playing in the background for Einstein, and you see sort of Einstein's sort of very dark sense of humor when in 1918, he writes to his estranged wife, he says, "I'm curious to see what will last longer, the war or our divorce proceedings. Both began essentially at the same time. This matter of ours is actually still the prettier of the two. Da ist unsere Angelegenheit doch noch die schönere." Right? So it's a very sort of dark joke that Einstein plays here. So on top of this, right? So there is this messy divorce, him not knowing whether to marry his cousin or the daughter of the cousin. And then there's also in 1917 he gets very seriously ill and he loses a sizable part of his body weight and is bedridden for 3 months. So, and that leaves its traces in his work. So if you compare Einstein's inaugural lecture in 1914 at the pinnacle of his fame when he comes to Berlin, so this is before the war, before the divorce, and before his illness, and compare that to a speech that he made in 1918 after those three things, you see a very striking difference, right? And that I want to show you. So in the inaugural address, he makes one of the most accurate and beautiful statements about the methodology of the young Einstein. So he says, the theorist's methods involves his using as his foundation general postulates or principles. Remember this distinction I made early on between principal theories and constructive theories. The scientist has to worm these general principles out of nature by perceiving in comprehensive complexes of empirical facts certain general features which permit of precise formulation. Now, if you think this formulation is a bit tortured, you'd be right. I mean, Einstein is a very lucid and clear writer, but he clearly chiseled away at this sentence to convey exactly what it is he wanted, right? So it's principles. How do you get these principles? You need to somehow be in communion with nature. It's not as simple as, well, you generalize from some obvious things that you have observed, right? And Einstein said this in a number of ways. This, I think, is the best way. Now, that is completely the opposite of what he said in Oxford. Completely the opposite, right? Remember, he says, we can discover the laws of nature by means of purely mathematical constructions. The creative principle resides in mathematics. Pure thought can grasp reality. Okay? Now move to 1918. So this is a speech he gave to celebrate the birthday of Max Planck. It's called Motivations for Research. And I want to read some passages from this. And so this is like very poetic prose. So I chose like a nicer font, which is completely unreadable on my screen here. So I hope that I can turn around and read it there for you. Okay. I believe with Schopenhauer, there you have Schopenhauer again, that one of the strongest motives that leads men to art and science is escape from everyday life with its painful crudity and hopeless dreariness from the fetters of one's own ever-shifting desires. A finely tempered nature longs to escape from personal life into the world of objective perception and thought. This desire may be compared to the silly dweller's irresistible longing to escape from his noisy, cramped surroundings into the silence of high mountains, where the eye ranges freely through the still, pure air and fondly traces the restful contours apparently built for eternity. It's a very sort of German romantic sentiment. So here's this famous painting by Caspar David Friedrich, The Wanderer Above the Sea of Mist, 1818, around the same time that Schopenhauer produces this work, the Die Welt als Wille und Vorstellung, that Einstein is thinking of here. And it's also around the same time that Einstein gets this bookplate made, right? Where again, you see this guy in awe of the stars whirling around him. I don't think that's a coincidence. So Einstein goes on, he says, with this negative motive, right? So far he's only talking about to get away from it all, right? With this negative motive goes a positive one. Man tries to make for himself, in the fashion that suits him best, a simplified and intelligible picture of the world. He then tries to some extent to substitute this cosmos of his for the world of experience and thus to overcome it. This is what the painter, the poet, the speculative philosopher, and the natural scientist do, each in his own fashion. Each makes this cosmos and its construction the pivot of his emotional life in order to find in this way the peace and security which he cannot find in the narrow whirlpool of personal experience. Okay? Now that was the evidence that I was referring to earlier. I mean, this sounds awfully like this Dear Mommy letter 21 years earlier. Right? So remember, let me read the key quote to you again. One creates a small little world for oneself, and as lamentably insignificant it may be, in comparison with the perpetually changing size of real existence, one feels miraculously great and important like a mole in his self-dug hole. But Einstein is not writing this as an 18-year-old to the mother of the girlfriend with whom he just broke up. He says this at the pinnacle of his scientific career, to his colleagues at a special session of the Prussian Academy to honor, one of their greats, Max Planck. Right? So I take this very seriously, and I think this is another factor why Einstein shifts to this different approach that, as I emphasized, didn't get him much, right? So now Einstein is not unique in this. I mean, in a way, you think of Einstein as this great revolutionary, but really his real talent was to do these principle theories, to with relentless logic pursue, if I believe this, what is going to follow? In terms of his imagination, he was much more of a 19th century guy. Right, and so he, like many of his contemporaries, he loved this Schopenhauer stuff. And so one of the other contemporaries that liked this is Thomas Mann, who puts this in his famous novel Buddenbrooks. So Buddenbrooks, like many of you will know, is this book about this family, in Lübeck. And at one point, Thomas Buddenbrook, the last of the upstanding members of this family, is lamenting the fact that his son does not want to, take over the business, but wants to become, God forbid, an artist. Okay, so he's completely despondent. He's sitting in the library of his house, and he takes this volume at random from the bookshelf. And Thomas Mann doesn't tell you what volume that is, but any reader would know that this is Schopenhauer. And he starts reading, and the consoling thought is, oh boy, we're all part of something much bigger, so there will be somebody else will be standing up for the values of the Buddenbrooks, even if that is not a real Buddenbrook. Einstein is using that same sort of consoling thought when he's sending out letters of condolences when people die. Don't worry, we're all part of something bigger, et cetera, right? So he's very much sort of a part of his time here, and this is where he gets these ideas, you use physics in part to just get away from it all, right? And as he put it, much more eloquently in the speech for Planck. So the moral of the story then is that we have Schopenhauer to thank or to blame, right, for Einstein moving from doing physics by putting the facts first and then trying to come up with principles to moving to a kind of physics like where you put the math first. And I would argue that that has like had a bad influence on physics, right? I mean, like just think of string theory. That's what they're doing, right? Put a bag over your head, write down pretty mathematics, and keep your fingers crossed that you'll hit on something that will describe reality. So so that's the moral. I want to add one caveat, right? And that is that the most extreme statement of this particular attitude is that 1933 Oxford lecture that I started from. And several of you may have already thought, like, well, that's a suspicious date, like 1933, right? This is when the Nazis came to power. So Einstein was actually in the US when Hitler came to power in January of 1933. He was on a ship back to Europe in March of 1933 when he received word that the Nazis has raided his summer house in Kaput looking for weapons, So as soon as he got back, he renounced his German citizenship, which he had reacquired. They didn't want it anyways, but now he renounced it. And he also resigned from the Prussian Academy before he would be kicked out by more conservative elements in that body. Okay? And before he went to Oxford, he went back to Switzerland and visited with his son. So I mean, this is really I find this like a very tragic picture. This is Eduard sitting behind this humongous ice cream cone. And this was the very last time that father and son saw each other, okay? So I think that it's not too far-fetched that when Einstein is like singing the praises of mathematics in Oxford, that these developments, the political and the personal, are sort of on the back of his mind. Thank you.
Thank you. I'm here with the microphone. We do have time for questions and answers. And I just want to say that was beyond all of the content and the storytelling. That was a fascinating combination of really hard physics and like soap operatic drama.
I think you mean it in the nicest way.
I do indeed. But I can see why you found it so fascinating that you studied it as you have. Let me get some questions from the audience, and I'll come around with a microphone for you.
Going back to the physics part of the lecture, and we were talking about inertia and gravity, seems to me, the way I've been thinking the past few years, is inertia is a very mysterious thing, which you can't really know what the heck it is. Is that true, or do you have thoughts on that?
Well, I mean, yeah, it is a mysterious thing. I mean, for Newton, sort of mass is one of the basic properties of matter, right? And so then there's this oddity that mass can mean very different things, like susceptibility to gravity or resistance to acceleration. But with E equals mc squared, it becomes like a completely different ballgame. So now, I mean, I've been talking about like mass increasing if you move very fast. So that's kinetic energy. But even if something is at rest, right, the mass corresponds to a certain amount of energy. So if you now like and so people are looking at, take a charge, and the charge is going to generate a certain field around it. And so that field contains like a certain amount of energy that is part of the mass of this particle. Maybe it's its whole mass. That was what people were thinking in the early 20th century. So with the development of like other theories of other interactions, like the weak interaction, the strong interaction, I mean, where this property of rest mass is coming from is not sort of black boxed anymore, as in Newton's theory. No, that it's just open for investigation, right? And so these cell fields, as they're called, contribute to this. And like, the most exciting development, or certainly the most hyped development in recent physics, like the discovery of the Higgs boson, right, also has to do with explaining why it is that things have mass, right? So I agree with you. And so remember I said, like, Einstein is good at just asking why questions, right? And if, like, in the 18th century, you would have asked, well, why is this mass? You think, like, well, just go play, right? Don't. But now, like in the 20th century, that has become like a very sensible question, and people are trying to answer this. And so the Higgs boson is part of answering that question. Why do things have mass? Yeah.
Hi. So I was very surprised to see that. I guess I don't know the history of science that well. I was very surprised to see that when he wrote his special relativity paper, that people still believed in the ether. So does that? I don't understand the timeline. So did Maxwell's equations and the stuff that's taught in electricity and magnetism in undergraduate physics now, did that all come about after Einstein?
No. So Maxwell's equations, or Maxwell never wrote down what you would now recognize as Maxwell's equations, right? But the equations that are equivalent to Maxwell's equations were written down by Maxwell in 1862. Okay, and Maxwell had this very elaborate picture of this medium. He thought it was cells rotating, idle wheels in between, and that macroscopically that would manifest itself to us as lines of force, the way that Faraday was thinking about them. Like Maxwell was trying to mathematize these earlier ideas, the 1830s of Faraday. So, very mechanical picture of the ether. Now, like my countryman, Hendrik Anton Lorentz gets into the act in the 1890s, and he is recognizing, like, no, this ether is something very different. In particular, like, this ether cannot move, and that means that through electric and magnetic field it can move stuff, but it itself is not moved, so it violates Newton's third law of action equals reaction. So, and then Lorentz says, well, so be it. It just means that this is not a mechanical system. But it is, like, there. And so Lorentz's theory is like the theory that Einstein is reacting against. And so Lorentz has already developed a lot of the formalism of special relativity. That's why it's called the Lorentz transformations, right? And so Einstein sort of takes the final step and says, out with this thing. And this was actually, like, seen as, like a very drastic step. Not nearly as drastic as Einstein in another paper, going back on the idea that light is always a wave and suggesting that sometimes it's a particle. I mean, that took 2 decades to get accepted. But even this idea that you now have to imagine that there is these waves waving in nothing was very hard to swallow. So one of Einstein's friends, Paul Ehrenfest, said it very nicely. So Einstein's theory is based on 2 postulates, right? The relativity postulate and something called the light postulate that says that light is always propagating at a fixed speed independent of the velocity of its source. So Ehrenfest joked, he says, like, well, we should actually, like, because that rules out the ether, right? Ehrenfest says we should actually add a 3rd postulate that says, I solemnly swear that the combination of the first 2 is satisfactory to me.
Thanks. So clearly Einstein's work bridged multiple fields between physics and mathematics, physical chemistry, but obviously his work transcended that into, the social element at the time. It seems our heroes today are, Steve Jobs and gentleman that started Facebook and these other things. Does Einstein have a modern day contemporary, would you say?
That's a good question. I'd hate to endorse Steve Jobs for this. Thank you. I will say a little bit more about, this is a bit dodging the question. But so about, like, Einstein's own role, right? So as I said, like, Einstein is famous as a pacifist. But one of the things that the guy I mentioned, like Robert Schulman, has shown very clearly is that during World War I, Einstein was actually not very politically active at all. Like, it's only after World War I that he gets very politically active. And so what is the thing that gets him? It's the anti-Semitism coming from German Jews. So, so Einstein is not a practicing Jew, right? But what really gets him is that, like, after the war, there is this influx from, like, Orthodox Jews from the East, and they're, like, really not welcomed by Westernized Jews, like people like Haber. And that really gets, so Einstein has this attitude, well, let's leave anti-Semitism to the anti-Semites. Right? And so he then starts championing the cause of, like, Zionism, like he's going on a tour in the US to raise money for Hebrew University, right? And so it's in that context that his political engagement develops. And then he also realizes that he can use now, he becomes this superstar after this eclipse expedition, that he can use that to pronounce on causes that are dear to his heart. And that he then continues to do for the rest of his life. So when he comes to the US, right, he's very grateful to the US that, they allow him in, but he is very critical of its society, right? So during the McCarthy era, he scandalizes the Americans, for instance, by writing a letter that gets published to spare the Rosenbergs, the death sentence, the Julius and Ethel Rosenberg. And the thing that gets him even more is not just the anti-communism, but the racism of American society. So it's always Einstein is speaking out in favor of these causes. He is in favor of weapons control. Of course, he writes the famous letter to Roosevelt, right, that supposedly triggered the Manhattan Project. In fact, as a matter of fact, they did all of nothing with this. That, they do what you do when you get a letter like that. You have committees investigating what to do, and not until Pearl Harbor are the Americans getting serious about this. But Einstein felt bad about his involvement there, so he gets after the war very much involved with disarmament, weapons control, and all of that. So I'm just hoping, rattling this off, whether another person today sort of comes to mind that is doing all that. Chomsky comes to mind, as somebody famous, in linguistics, who also has these, all these political causes that he's championing. I'm blanking on other near contemporaries at the moment.
In listening to you talk about Einstein, I hear a story of two different characters. Obviously, it's much more complex than that, but there's sort of the very it's the humility versus the hybris. It feels like, or the hubris. What do you? I'm curious about whether you feel, if you feel like one was a stronger driver in his ultimate sort of perspective on the world, on the unified field theory, on.
No, I like that. I like the, so humility versus hubris, and what won out, right? It's hard to say. So I think that, so you would think when you look at these statements sorry for the Lord, but it's, but at the end, it's not the sense I get. So there's Einstein is hardly the only physicist being arrogant, right? I mean, there's people who outdo him on that score, by miles. So the famous joke about Wolfgang Pauli coming to heaven and saying okay, God, tell me the secret of the universe now, right? And God goes to the blackboard, starts writing, and Pauli says, I tried that won't work. So Einstein is not like that, right? So he always. So I would think if I had to put the choice, I would say humility. Because certainly early on, right? I mean, he makes his success out of acknowledging that he doesn't know how the quantum world works. But even when he is on this crusade, right? I'm going to do this unified field theory. There's also all these self-deprecating comments where he says, well, I'm hoping that one day this will replace quantum theory. But, he knows that the odds of that happening are rather slim. And he says, look, I've sort of earned it, right? To do so yes, let these other people do quantum theory. I'm going to do my own thing, right? And even if it doesn't get very far, so be it. Right? So no, I would definitely say, so there is this element of hubris, definitely, but the humility is the stronger component there. Yeah.
I can think of lots of questions, but one I had was you had dismissed the proposition that his wife at the time was involved in the miraculous year, despite you yourself saying that if you have a singular cause or for something you should be suspicious. So
yes.
Could you comment on that?
Okay. I mean, the reason I feel strongly about this particular one is that I don't think Mileva Maric is served by trying to now cook up stories and make things out of whole cloth about what she did about special relativity. The tragedy of her life, I think, is that she was one of the first women to come out of Serbia to get higher education, and then she got pregnant. Okay, and that was the end of it. And so then, this partnership that Einstein envisioned completely fell apart. So that is the real that's I think like her story. And so historians have looked very hard to see, like whether she like collaborated with Einstein on things. And sadly, the answer is like there's not a shred of evidence that she did. Of course, like absence of evidence is not evidence of absence, right? But all indications are that tragically she was not involved in this. And then so for a while, like there was like a PBS documentary like a number of years ago, and the entire premise of that show was that like Mileva Maric was actually the brain behind like the Miracle Year, right? And so that got so much criticism that PBS like a year later took down the teaching materials that they posted on the web for like teaching people in high school this kind of stuff. And I've always been sort of amused by this camp, like contradicting itself. Like so some people want to say that Mileva did it all. Well, she did the math, okay, and Einstein did the conceptual stuff. And then others say no, she did the conceptual stuff and Einstein did the math. I mean, and so I think that's sort of indicative that like my sense is in that case, like, I mean, I totally take your point that it looks as if, I'm here like, trampling over my own dictum of like not trusting like monocausal and very, definite stories. But here I have a strong sense like, there's just nothing there. And all it does is to, by arguing over this, like you take away what I think is the real story here. That like it doesn't make Einstein look very good. That he did not try to realize this partnership that they were envisioning when they were students together at the ETH. I'll tell you one more anecdote about this thing. So you've heard the story about Einstein's brain, right? And so at some point in the late 90s. There was like an article in the Lancet where they had discovered some abnormalities in Einstein's brain. And so I was working at the Einstein Papers at the time, and of course the phone was ringing off the hook. And we had agreed, like, okay, our line is going to be, if you want to understand like Einstein's genius, don't look at the gross anatomy of his brain, look at his papers. Right? It's a rather self-serving answer, but... So at one point, like a woman from the BBC calls and asks me. So I was, we're taking turns. I take this call, and she says, "Is it true that Einstein's wife came up with special relativity?" I said, like, "No, that's not true. But I'm a little worried, a little puzzled that you're asking me this today because, like, the topic of the day seems to be not that, but this question about Einstein's brain." She said, "No, that's what we're interested in too. But our angle is that they looked at the wrong brain."
All right, I'm up here in the back with a question for you, Michel.
Hey there. Thanks for the talk.
Yeah.
It's really good, actually. Throughout the talk, I noticed that there was a focus on kind of dualism. So electricity and magnetism, inertia and gravity, hubris and humility, as pointed out by some. And the question about what is a modern contemporary and what's an example of who that would be today, and it seems that in that the resolution of that dualism comes great insight, but that without that struggle it doesn't happen, and I'm not saying this very well, but I think Steve Jobs is a polarizing figure because he was so singularly focused on what he was trying to do. The same might be said of other great people, including Einstein. And what I guess my question is, in your research into other scientists as well who have been as successful technically, I guess, have you seen similar things like that, where that so deep focus on the purely intellectual and the neglect of the emotional?
That tenacity I've seen in other people. So in terms, like when you ask about sort of this, like the polarity, the duality, I'm not so sure. Like, I mean, I think that is largely also just an artifact of setting up the story, right? And so, like, in a way, like, when I talk about this unification, I wanted to give you a sense of, like, that Einstein didn't just out of nothing starts wasting his life coming up with a grand unified theory, but that it really it's a sort of a logical next thing to do, given what he had done with relativity and with both special and general relativity. So on the duality, I would have to think about it, how. But it's definitely the case that there is a sort of a single-mindedness of purpose that you see in Einstein, and you see this very early on. Remember, I told you that he flunked his entrance exam at the ETH because he could not be bothered, right, to bone up on subjects that that had no interest for him, right? And so during World War I, right, when afterwards people like to sort of point to the few things he did as a pacifist, in fact he's just hunkering down and trying to work on the general theory of relativity and ignoring a lot of things. So one of the things I read in a biography of another very famous scientist, Lise Meitner, right, the discoverer of nuclear fission, even though Otto Hahn won the Nobel Prize for it. So she knew Einstein when in the late 10s. And I was very surprised when I read a statement by Lise Meitner complaining to somebody else, saying would it kill this Einstein character to pick up a newspaper every once in a while? So that's how single-minded he is in pursuing this, right? And so if I add the other thing, and this is that you see in many scientists. The thing that I think is rarer and that you see very clearly in Einstein is that there is a certain flexibility, right? So he gets very tenacious about something, but then when somebody gives him a knockout argument against it, he just drops it like a hot potato. And a lot of other scientists, when it's their baby, their pet idea that is being killed, they will tend to sort of squirm and trying to find ways to hang on to it. And Einstein was very proud that he didn't do that, right? So at one point he wrote to a friend, he says "Oh yeah, well that's funny with that guy Einstein. Every year he renounces what he'd written the year before, And Einstein thought that it was great that he was doing this."
I'm sorry, I have to point out that that's the second argument for the usefulness of his wife. That if she wasn't useful, he wouldn't have kept her.
Well, I think we've just come right to the end of our time here. I want to say thank you so much to Michel Janssen for illuminating the life and times of Einstein. And please do join us next month to learn about mammoths and mastodons of the late Pleistocene era.